Hello, this is 6.3 notes, the first part of it. So 6.3 broken up into two lessons. So this is part one. I did fill out the success criteria for you, but you do need to make sure you fill out the learning target and your name and stuff before you get started. Starting with the vocabulary words, we have radicand. Radicand is the number underneath the radical. In my little example, it's the 64. And then we have simplest form of radical. This is something that we're going to be working on all throughout this section, is just simplifying radicals. We can think of that kind of like simplifying fractions, but with different rules. And we'll get to the rules in a minute. Rationalizing the denominator is whenever you get the radical out of the bottom of the fraction, or you no longer have a radical in your denominator. Conjugates, this, like so that and that are conjugates. So these two things are conjugates because they're the same. They're binomials that are the same, or they have two terms in it, and the terms are the same except for instead of a plus sign we have a minus sign. So one with a plus and one with a minus. So our rules to simplify radicals, we have three of them. The radicand, or like the number under the radical, cannot be divisible by a perfect square if you're using square root, or perfect cube if you're using cube root, or perfect fourth power if you're using 4 as your index. The radicand cannot be a fraction, and there cannot be a radical in the denominator. So all three of those things have to be taken care of in order for a radical to be simplified. Example number one, it says simplify each expression. And we have part A, we have the square root of 147. So whenever I have that, I'm going to use my list of perfect squares and perfect cubes, which you will need this as well. So obviously you could find these out, but having this reference handy is good for you. So 4, 9, 16, 25, 36, these are all the perfect squares that I'm going to use in order to do these. Also, we're going to add one more in here, x squared. So x squared, or a squared, or n squared, or any variable squared is also a perfect square. So the way we do this, we're trying to simplify the radical, so we have to follow the three rules. Rule number one says this cannot be divisible by a perfect square. So that means any of these numbers, 144, 121, 100, 81, none of those can go into 147 in order for it to be simplified. So if we can take 147 and divide by any of those numbers and get not a decimal, so if I can divide by 81 or 64 or 49 or 36 or 25 or 16 or 9 or 4, then it's not already simplified and we have to simplify it. So based upon that they're telling us to simplify it, then we're probably going to be able to. So I'm just going to take my calculator and I'm just going to trial and error, start with the number I think might go into it. Obviously these numbers that are larger than 147 aren't going to work. Any number that's over half of 147 is not going to work. So maybe I would start with 64. You want to try to find the largest perfect square that goes into it. So that is a decimal, so that didn't work. So then I would just keep going down my list, and the next perfect square on my list is 49. And I did get a whole number, so that means that 49 times 3 is equal to 147. So I'm going to split this up into 49 times 3. And then from there I just treat each piece separately. So 49, can I do the square root of 49? So for example, can I put in square root of 49 and get a number? And I can. It's 7. And that's kind of the point of these perfect squares. We can do that. So we kind of treat the pieces that we can do. We solve the parts we can do. So square root of 49 is 7. And then the parts that I can't do, I'm just going to leave. And then that is my answer. Part B. We have square root of 25x to the 5th. again, I'm just looking to break this up into pieces that I can solve and pieces that I can't solve. You notice that 25 is on my list, so it's already a number that I can solve. So that doesn't need to be broken down to 5 times 5 or anything like that. So I'll just leave it as 25. But x to the 5th, we have to realize that that's just 5 x's being multiplied. And so I am going to break that down. So the way I'm going to do that is I have 25 times x squared, that's 2 of them, times another x squared, that's 4 x's, and then times the last x. And so 1, 2, 3 pieces I can solve. I know what the square root of 25 is, it's 5. I know what the square root of x squared is, it's x. I know what the square root of x squared is, it's x. I don't know what the square root of x is, so I would leave that like this. And then I can clean this up a little bit, and my final answer will be 5x squared square root of x. Example number 2, it says simplify each expression. And then we have a radical here, and our rule number 2 says we cannot have a fraction underneath the radical. So the way that we, alleviate that is we just turn it into 2 radicals, like that. And then we're just going to solve as we can. So if I can do anything with square root 11, I'll change it. But if I'm looking at my list of numbers, I notice that 11 is prime. So that means I'm not going to be able to do anything with it. So I'm going to leave that as square root of 11. And then I'll notice that 36 is on my list, and it says it's 6 squared. So that means the square root of 36 is 6. So then that is my answer. Part B, same thing. I have a fraction, so I need to change it into 2 different radicals. And then I'm going to look for perfect squares that are divisible, and it looks like 25 is on my list, and so is x squared. X squared, a squared, n squared, doesn't matter the letter, it's the same thing. So square root of n squared is just n, and square root of 25 is just 5. So that is my answer. Example number 3. Again, we're simplifying expressions. This time we have cube roots, so instead of our perfect square list, we're going to look at our perfect cubed list. So we're not worried about this one, now we're worried about perfect cubes. So I have the cube root of 135, and I'm not allowed to have a perfect cube that's divisible, or 135 is divisible by, so I'm going to check these. Obviously, the numbers, bigger than it aren't going to work, and it's got to be at least, less than half the size for sure. So I might start with 64 if I think that will work. So 135 divided by 64, and it's a decimal, so that didn't work. So then I would just keep going down my list until I found one that does work, and 27 works. So 27 times 5 is 135. That's what that tells me. So I am going to break that 135 down into 27 times 5. Then from here, I'm just going to solve the parts that I can solve. I know the cube root of 27 is 3. I have my little cheat sheet. So that's 3, and then the second part I can't solve, so then that is my answer. 3 times the cube root of 5. Part B. I have 3 times the square root of 8x to the 4th. Now, I have a square root, so I'm going to use perfect squares. So my index is 2 and not 3, so I am looking at my perfect square list. I'm looking for a number that goes into 8, and I have 4 here. I know that 4 times 2 is 8, so I am going to break that down into 4 times 2 times x squared times x squared. So all of the parts that I can solve, I'm going to solve. I know the answer to this is 2, the answer to that is x, the answer to that is x, and I don't know the answer to square root of 2, so I'll leave that as square root of 2. These are all being multiplied, and I have that 3 out front that's also being multiplied. So this is my answer, but I'm going to kind of clean it up. 3 times 2 is 6, and x times x is x squared, so 6x squared times the square root of 2. Is my answer. Part C, we have a cube root and we have a fraction. We're not allowed to have a fraction, so anytime we have a fraction, we just split it up into 2 radicals. And then after I do so, I will notice that I know the answer to this one. 1,000 is on my list. 10 cubed is 1,000, so that means negative 1,000 has to be negative 10. So I solve the part that I know how to solve. This is y squared, and that's not on my perfect cube list. For perfect cubes, I would need x cubed. So I would need 3 variables multiplied together to be a perfect cube. This time I only have 2, which means I don't know how to solve it. There's nothing I can do to change it, so that just stays put. Part D. Again, we have a fraction, so we're going to split it up into 2 pieces. 343 x to the 8th over cube root of y cubed. So 343, I'm going to look to my list for the largest number that goes into 343, and actually it's on my list, so I don't need to break it up. I know that the cube root of 343 is 7. So I am going to break up the x to the 8th though, so I'm going to switch this up into 343 times x cubed times x cubed. That's 6 x's, and I need 2 more, x squared. And I can go ahead and solve this part on the bottom. The cube root of y cubed is just y. So for there, I'm going to solve the parts I can solve here. So I know the answer to this is 7. I know the answer to that is x, and I know the answer to that is x. So I have 7 times x times the cube root of x squared all over y. Now, the only thing I'm going to change is x times x is x squared. So I'll clean that up a little bit. 7x squared times the cube root of x squared all over y is my answer. Example 4 says simplify each expression. I have square root of 7 over square root of 2. So the rule that I'm breaking here is I'm not allowed to have a radical in the denominator. That was part of my rules. And I do know that if I take the same thing, so if I take any number, so square root of 10 times square root of 10, I get 10. Or square root of 4 times square root of 4, I get 4. I know that as a fact, and so these are the facts that I'm going to use in order to help me solve these. So I need to get rid of this radical on the bottom. I have square root of 2 on the bottom, and I need to get rid of it, so I want to multiply by square root of 2. But I can't change the expression, so I need to multiply by something that's equivalent to 1. So if you multiply anything times 1, it doesn't change it. It might change the way it looks, but it doesn't change it. And I know that square root of 2 over square root of 2 equals 1. So anything over itself is equal to 1. So this factor right here is equivalent to 1. So when I multiply by 1, I'm not changing the value. Multiply these across, they're both in a square root, so that just becomes square root of 14, and then this becomes 2. And then that's my answer. Square root of 14 is simplified, so I'm finished. Part B, I have 5 over the cube root of 4. So I have a cube root on the bottom. I'm not allowed to have that. So I'm going to try to make that into a perfect cube. So I have 4, and I'm going to look at my list of perfect cubes. And I have 8 on my list. I know that 4 times 2 is 8. So what I'm going to do is I'm going to multiply by the cube root of 2. And by doing so, that changes the bottom into cube root of 8, and the top becomes 5 times the cube root of 2. Well, now I know the answer to cube root of 2. I know that that's just 2. So I've just I've chosen to multiply by that because I know whenever I do that, I'll be able to get rid of the radical. So it's kind of almost like a puzzle. You have to figure out what you're going to multiply by in order to be able to get rid of the cube root. Example number 5, it says simplify, and we have an expression here, and we have a radical in the denominator. We're not allowed to have a radical in the denominator, but unfortunately this time we have a plus 1 on it, which is not part of the radical. So if I were to multiply just by this, square root of 3, whenever I were to multiply this, I'd have to get 3, but then I'd have to distribute it, and it would end up being 3 plus 1 times the square root of 3, and then I'd be right back to where I started with another square root. So we have to use what we call the conjugate in order to do that. And I'm just going to kind of show you. Whenever I multiply by the conjugate, again, I have to multiply the top and the bottom by the same thing so that it doesn't change the value. But whenever I multiply by the conjugate, I'm distributing, and I get this times that is 3, and then this times that is negative 1 root 3, and that times that is plus 1 root 3, and that times that is negative 1. And then from here, these two terms are going to cancel each other out. So all I'm really left with is 3 minus 1. So this is what I'm going to choose. This is why we're choosing the conjugate. So when we multiply by the conjugate, all we have to do is multiply the first terms and the last terms, because the two terms in the middle are going to cancel each other out. That's why we're choosing the conjugate, in order to get them to cancel. When we do that multiplication, we get 3 and minus 1. And on the top, I have to distribute on the top as well. So 4 over square root of 3 minus 4. From here, I'm going to simplify that down to 4 root 3 minus 4, all divided by 2. And then lastly, we can think of this as an x. So if I had, or almost like it's a variable, if I had this, I would just see if I can divide the numbers. And since 4 does go into 2, I would be able to change that to 2x minus 2. So similarly, I'm going to be able to change this into 2 root 3 minus 2. And then that will be my answer.